The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to today's webinar, Introduction to Protection and Control. My name is Tracy Noble, and I'm with ABB Power Systems. I will be moderating today's webinar. Before we get started, I wanted to go over a few housekeeping items with you. All participant audio will be muted during the event. If you would like to ask a question during today's webinar, please use the question box or the chat box in the GoToWebinar control panel on the right side of your screen. We will answer as many questions as possible throughout the event and at the end of the event, but please do ask your question as soon as it comes to you so that we can respond to it. Today's webinar is being recorded, and a link to the recording will be emailed to you following the live event. Feel free to forward the link on to people you know would benefit from this presentation. It is my great pleasure to introduce Elmo Price. Elmo received his BSEE from Lamar State College of Technology in Beaumont, Texas, and his MSEE degree in Power Systems Engineering from the University of Pittsburgh. Elmo began his career with Westinghouse in 1970 and worked in many engineering positions. He's also worked as a district engineer located in New Orleans, providing engineering support for Westinghouse Power System products in the South Central U.S. With the consolidation of Westinghouse and ABB in 1988, Elmo assumed regional responsibility for product application for the Protective Relay Division. From 1992 to 2002, he worked in various technical management positions responsible for product management, product design, application support, and relay schools. From 2002 to 2008, Elmo was a regional technical manager providing product sales and application support in the southeastern U.S. Elmo is currently Senior Consultant for ABB, a registered professional engineer, and a life senior member of the IEEE. He is a member of the IEEE Power System Relay Committee and the Line Protection Subcommittee, serving as a contributing member to many working groups. He has 2 patents and has authored and presented numerous industry papers. And now it is my great pleasure to introduce you to Elmo. Elmo, take it away.
All right. Well, thank you, Tracy. Today we're going to cover an introduction to protective relaying, and that's exactly what it is. There's really not much technical here, but we're going to give you a general overview and understanding of the role of relays in the protection and control. We will define relay classifications to you, review common relay applications, help you understand relaying philosophy, and review basic principles of protection. We will also finish up by reviewing the IEEE device function numbers and IEEE and IEC symbols. So the big question is, what is relaying? And here I'm going to give you a little bit of a history lesson, but first, if you look in the dictionary, you might see these definitions: an act of passing something along from one person or group or station to another, a supply as of forces arranged beforehand for successive relief. Many of you are familiar with the Old Westerns and the Pony Express. A number of persons who relieve others in some work, and then, of course, an electrically operated switch that responds to current or voltage in one circuit to switch on and off a current in another circuit. All right, let's go back to the word and a little bit of a history lesson here. Is relay. It was derived from a French word, relays, which at that time meant replacement. The term relay was first applied in 1830 to a team of fresh relay horses that pulled horse vans, which were actually rail cars on a wooden railway, between Baltimore and Elliott Mill, Maryland. This was operated by the B&O Railroad. And actually you can go online and see a town there named Relay, Maryland, where this took place. And the term also applied to the station where the work horses were changed for fresh horses to continue the journey. Of course, in the Old West, we had stagecoaches and relay stations for stagecoaches. And in 1860 and 1861, we had the Pony Express that moved mail across the West in relays. At about the same time, electromagnetic technology was evolving. Well, we go back in history, and Joseph Henry invented an electromagnetic device, later to become known as the telegraph electromagnetic, but it was an electromagnetic device which he could control from a long distance away, operate the device, and on the secondary of the term of the magnetic device, he could pick up or switch in a DC power that would operate a load, and he primarily used this to lift heavy magnetic loads. And as most of you probably know, Joseph Henry was an American scientist, and he has the term Henry, which is applied to a unit of inductance, which is used commonplace today. At about the same time, you had an American, I would say, an artist. He was known as the Leonardo da Vinci of the Western Hemisphere, but he had wide, broad capabilities of being an engineer, artist, and so forth. And he took Joseph Henry's technology and made it into something practical, because at that time there was a lot of work going on in telegraphy, and to compete, if you will, with the Pony Express, where you could get messages delivered from somewhere to another location pretty fast. So Samuel Morse came up with the idea of the sounder, where you operate a key and it creates a sound, or you can go over a long distance and operate a repeater, which would repeat it into a secondary circuit, on and on. And he invented the Morse code, as you are what he's most prominently known for. That was some basic action. So somewhere in about that time frame, recognizing the similarity of function between relay horses, or the Pony Express changing the horse to get mail out to the West fast, and the telegraph repeaters and sounders, the telegraph electromagnetic device, some engineer started calling it a relay, and that name was pretty much adopted. And so the first electrical relays were used in long-distance telegraph circuits. The electric power industry didn't begin to take off until the 1880s, and the need for protection evolved with the development of the power system and the experience gained through experiencing system faults. It began where they did nothing and just let the faults occur, which usually resulted in throwing fan belts off of steam supply engines that would be driving the generator or something like that. And then they began adding intentional thin wires, intentional weak links, where the thin wire would burn up during a short circuit condition, and then fuses were invented. Problem with fuses were their availability, and often there were maintenance shortcuts. Taken from a 1922 book, you can see the view of an engineer. He says the improper replacement of fuses is one of the deepest rooted evils in the electric industry, and that practice even still continues today. But anyway, electromagnetic operated switches were built, but still there was no fault location discrimination. And then emerged the application of the telegraph relay technology. And so over the years, from those early days, we've seen an evolution of the electromagnetic technology itself, from the early relay devices to a period where solid state had a short life existence, and then into the microprocessor area, to the devices that we have today that contain not only protection but control as well of everything in the substation. So with that, a definition is a relay is a device that responds to a measured quantity, voltage, current, heat, pressure, vibration, from one system and switches current into another system, usually an electric circuit for the purpose of protection and control. That was a definition from the 20s, and today perhaps a more modern definition would be protective relays or devices that are used throughout the electric power system to detect abnormal and unsafe conditions and initiate corrective action. There's classification of relays defined in IEEE standard C37.9. They're defined by protective relays, detects intolerable conditions and defective apparatus. There are monitoring relays to verify condition in the protection and or power system, generally providing some type of alarm for abnormal conditions. There are reclosing relays, which establishes the closing sequence for a circuit breaker following a protective relay trip. There are regulating relays which operate to maintain operating parameters, maintaining the voltage level with a voltage regulator, for example, or a voltage regulating tap changer on a transformer. You have auxiliary relays, which operate in response to other relay actions to provide additional functionality, and then synchronizing relays to assure that proper conditions exist on two sides of a breaker before closing it. You have classification of relays by input, whether the input's current, voltage, power, frequency, temperature, pressure, flow, vibration. You have classification of relays by performance characteristics, them overcurrent, over-under voltage, distance, directional, inverse time, definite time, ground or phase, high or slow speed, current differential, phase comparison, directional comparison, and we'll talk about a number of these later. You have classification of relays by their operating principle, be them a current balance, whether they're percentage biased or multi-restraint devices. They could be a product, thermal, or some type of comparator, or let's call it a phasor comparator. Then you have phase or magnitude. And then you have classification of relays by technology. As you saw, you had the initial period of electromechanical relays, a short-lived period for solid state or static relays, and of course the modern microprocessor-based relay of today. Relays operate not alone, but as part of a team. The relay that are most often used require being able to read the system quantities, voltage, current, frequency, etc. And to do this, you need the appropriate sensors like a potential transformer, coupling capacitor voltage transformer or some type of transformation from primary system voltage to a secondary voltage, which would be safe for the relay. The same for the CTs, being able to read the current that exists up at the higher potentials and being able to read them at the secondary. Of course, you also have the switch or circuit breaker that you are trying to control. You're going to make some measurements and then operate the switch or circuit breaker to provide some type of corrective action. And you have the DC power supply, which must be maintained such that the relay stays in operation, and of course the interconnection of all these devices. Next slide, Tracy. Okay, and a simple interconnection here is that you have your CTs on the primary system, your relay, you do some detection, and you have a battery source and a breaker to control. Well, let's talk a little bit about the principles of relay application. The first and foremost is the selectivity. As I mentioned before in the history, initial protection was not very selective. You either tripped or didn't trip because the system you had burned down or you had a fuse blow or something like that. But the selectivity deals with minimizing the impact on the power system whenever you have one of these intolerable conditions. And the relay trips, you only want to trip and control just the minimum amount of area of the system to have that impact. The second point is reliability, and of course reliability is a balance between dependability and security, and speed. Speed is based on need. In some cases you need very high speed to maintain system stability. In other cases speed is not near as important. Of course, simplicity. There are those when microprocessors emerged, we started doing everything in one box, and people complained about complexity. Today with 61850 in control, people still complain about complexity, but I will challenge the young people in the audience that once you learn a modern relay, go back and try to work with some electromechanicals, and you will get a different picture of complexity. Then, of course, there's always the economics. Let's talk a little bit about reliability, because important in your jobs, of course, is providing reliable protection. And it's a balance between dependability and security. And dependability is the certainty of correct operation in response to system trouble. You want to be certain that you've detected the event. And then security is the ability of the system to avoid undesired operations with or without fault. And to give you an illustration of dependability and security, we can see for dependability, if we have two relay systems, that if one doesn't detect it, the other one most likely will. So your certainty of operation in response to a system problem has certainly increased. While at the same time, you looking at that, you can see how the security may decrease. Now, if you look at the security and you put them in series, it requires both main 1 and main 2 to operate. Therefore, the ability of the system to avoid misoperation with or without fault. So that if one has a tendency to misoperate for a certain condition, it will not. Whereas if you look to the figure on the left, you have more possibility of misoperation. So anyway, this is just an illustration between dependability and security, and you must always recognize the balance between the two. So in talking about selectivity, we can refer to the zones of protection. We have zones of protection for generators, transformers, buses, transmission lines, and motors. There you go. We'll start off with a simple power system here, where we have station A, B, C, and D, and we will first show our zones of protection for the generators. And in both cases, the generator would operate the breaker if it's a breaker tied directly to the generator. It would of course trip that. If it's a generator that's connected to a breaker through a transformer, it would trip the transformer breaker on the high side. Then we add the next level of protection, which would be the transformers. And as you can see, the transformers would either have a breaker on each side to isolate problems, or in the case on the left, where the generator and transformer are all in one zone. Here we begin looking at the bus and the overlapping zones. But here is shown the bus protection that these are connected to. And then, of course, the next one would be the line protection, as shown there. And as you see in all these illustrations, of the overlapping that exists between the zones, the common breakers that exist. Okay, and finally the load. All right. And if we notice that as we did this overlapping, it says CT for red zone. It's not very red, but anyway. You have the CTs that are going to be protecting a zone on the opposite side of the breaker. That is the normal convention. The normal way a dead tank breaker at least would be applied. Next slide. Basic protection principles. We're going to address these characteristics, if you will, that I have shown on this page. Definite time, overcurrent, inverse time, direction, distance, differential, phase comparison, directional comparison. A definite time is a definite time overcurrent is as it states that at a set time, and this time could be instantaneous or some set time, at a set time for any current at or above the pickup level, the relay would operate. So that's its characteristic is a straight line. Then you have the inverse time characteristic, such that the lower the current, let's say the lower the current, the longer the time it takes it to operate, and the higher the current, the faster the relay will operate with that inverse characteristic. And what that inverse characteristic is good for is to apply coordination, and that this this will be covered in more advanced subjects, but basically coordination, the inverse characteristics allow the relay at A, or let's say the relay at B, to operate first for a fault at the shown location before the relay at A operates. Then you have overvoltage and undervoltage protection, and that's just basically shows you the two operating regions. You have your voltage pickup level. If it's an undervoltage relay, it operates where the voltage is under that value, or it operates where the voltage is over that value. And you also have a voltage balance, where you measure the voltage on each side of an object, and this is quite often used in capacitor bank protection. But you measure the voltage at 2 points and measure their differences, which shows the difference, which shows the voltage drop across the object. Directional relaying. What directional relaying requires is some type of what's referred to as polarization, but it's a reference quantity that maintains its relative direction regardless of if the fault is on the upstream or downstream or high side or low side. Regardless of where the fault is located, the phasor of that polarizing quantity is always at the same angle. And then you have an operate quantity, which would be in one case here shown as forward. It would show the fault as forward when compared to the reference quantity, or it would show the fault as reverse when compared to the reference quantity. So that's the key for directional relaying. Here are some basic protection principles. You have a reference quantity and an operating quantity, and you have a boundary condition such that for multi-phase faults, we show you some quantities that the I operation would be the phase current, X is equal to A, B, or C, and the polarizing quantity would be the voltage that is in quadrature to the operating current, or let's say the current you're measuring when there's no fault. It would be the voltage that is in quadrature to that, or in what they say cross phase. In other words, if you're looking at IA at unity power factor, then you would be using voltage VC. Ground faults, oops, you need to go back. Ground faults, the operating quantities generally are 3I0 compared to 3V0, or it could be 3I0 compared to a polarizing current, usually taken from a transformer delta or neutral, or it could be negative sequence quantity, where the operate quantity is 3I2 and the polarizing quantity is 3V2. Okay. Distance relaying is often referred to as impedance relaying, but it's being able to measure the impedance to the fault and making a decision whether that's within its zone characteristic or not. And you operate, it says three-phase system loops. The three-phase system loops are the the AB, the BC, the CA loop, but also the A to ground loop, B to ground loop, and C to ground loop. And you have a phase comparator principle that generally is used to determine whether the fault is within the zone or external to the zone. You're able to detect both phase and ground faults, and utilize both the positive and zero sequence transmission line impedances to do so. Now, the basic principle of a phase comparator is that you have two quantities here. I show S1 and S2, and you're going to compare those angles. And what I'm shown here is that with S2 in the given direction in the diagram here, that if S1 is within 90 degrees leading or lagging of S2, you're always generating operating torque, and you'll eventually get an operation if it's lagging or leading by more than 90 degrees, you'll get a restraining torque. Typical distance characteristics. For a mole unit characteristic, which is self-polarized, you have the circular characteristic that goes through the origin and the set reach. And the set reach is, of course, the diameter of the circle there that I show on the impedance plane. The impedance plane shows both the resistance and reactance direction. Basic differential protection, current differential protection. What you do is measure what goes in and what goes out. It's just a fundamental principle a node or Kirchhoff's law. What goes in has to equal to what goes out, and what you're doing is measuring the difference between these quantities. And if you get an operating quantity of a sufficient amount, then you end up operating. And like we say, if it's an external fault, the values would be equal and the I operate would be 0. If there's an internal fault, the I operate would be quite large. And it's applied to generators, motors, transformers, transmission lines, buses, shunt reactors, so forth. Types of differential measurement you have. Here I show where the number of buses are all summed up. The ground fault on transformer windings, that's commonly used today, referred to as restricted earth fault detection, but you measure the the current in A, the current in B, and the current in Z. They should add up to whatever 3I0 is, and you compare that quantity with the actual 3I0 flowing in the neutral. And you have high impedance bus protection, and this is where you add up all the buses. Where you add up all the buses, the currents of all the buses sum up, and you flow through a differential measurement. Normally, what goes into a bus must come out of a bus. So the summation of ID you see at the bottom is I1 plus 2 plus 3 plus 4 would typically be 0. But if there is a difference, that difference goes through a very large resistance, producing a very large voltage, which is immediately picks up and provides very high speed, reliable bus protection, and this is referred to as high impedance bus protection. You also have different types of differential measurement. One is that you have some type of restraining quantity, and the restraining quantity is plotted against some difference quantity, and you have some slopes. You have a minimum operate level of the slope. Then you have, I show a lower slope, which is referred to as M2, and a higher slope, which is shown as M3. And that shows you the basic difference between the restraining region and the operating region for your IDIF compared to iRestraint. And then you have another one, which is sort of a directional criteria, where your I operate is compared by angular relationship to the reference quantity, IREF. Okay. Your line differential relay usually involves some type of digital channel to transmit the information. In older relays, it was actually conductor. But anyway, you basically transmit the waveform from one end to the other, and at the local end where you're receiving the wave, the voltage or current information from the remote end, you compare the two quantities to determine whether it's internal or external. Of course, for an external fault, the summation of the two quantities would be 0, and for an internal fault, there would be some value there to the internal fault. Next, okay. Then you have directional comparison relays, and these are used with either instantaneous ground overcurrent or impedance measurement. And what you do is you're really, as the name implies, you're doing some type of comparison of fault direction, where the information from each end is transmitted to the remote end as to how it sees the fault. Is it forward at one terminal, or is it reverse at one terminal? And each terminal takes the information it receives and makes a decision whether to operate. For example, a permissive overreach transfer trip, POTT sends a permissive for an external fault, and at the faulted end where the reverse fault is seen, the POTT does nothing, so there is no trip. A permissive underreach transfer trip scheme sends a permission, but again, since the fault is reversed, the PUTT does nothing. The unblocked system sends an unblocked signal to allow the local end to operate, but the unblocked, seeing a reverse fault, it does nothing likewise. And then a blocking signal is received at the left end because the remote end sees a reverse fault and sees a blocking signal. And so that's basically how they would operate for an external. For an internal fault, POTT sends and receives permission at both ends. PUTT sends and receives permission. An unblocked sends and receives an unblocked and trips. And blocking system does nothing in regard to sending any information, so they both see a forward fault and end up tripping. Now, those were the basic schemes, and what we're going into now is documentation, if you will, that you really need to use to analyze system faults. Now, typically I don't show too much of this, or you don't see a whole lot with more modern relays, but you do have a real large installed base of electromechanical relays. So I'm showing you some electromechanical internal schematics. Each electromechanical device has an internal schematic that shows you the coils that operate, like the induction unit, the indicating instantaneous unit. There may be a directional unit. There is an indicating contactor switch which operates whenever the relay operates to give you a target, because in those days we didn't have everything on digital fault recorders, and you had to depend a lot on these indicating contactor switches to get information about what operated and did not operate. And then there's also the legend of the test switch, the current jack, and the terminal numbers. And you have your trip output contacts, and these devices are shown on other diagrams as well. Next. This would be your external schematic showing the connection to the power system, and you would also have in the schematic information would be the external connections to the power system, but the terminal markings that show the connection to the actual relay, or the internals of the relay. Next. And then you would have the external DC schematic again, where this is the, if you will, the logic diagram of an electromechanical relay. You have your indicating contactor switches, you have your device operating contacts, and shows what needs to operate to trip the appropriate circuit breaker trip coil, the 52TC. And of course, more modern relays are provided with logic diagrams to show you various elements and how those elements are combined together to operate certain logic quantities. The IEEE device function numbers is, you want to refer to the standard C37.2, originally, not originally, but last revised in 91, but revised to just recently. But a device function number with an appropriate prefix and suffix where necessary is used to identify the function of each device in all types of switchgear. So that's why you hear overcurrent relays, for example, an instantaneous unit might be referred to as a 50, which would be the device number, or a 50N, which would say that it is a measuring the residual current, for example. And then you would have a 51, which says it's an instantaneous unit. I mean, excuse me, a inverse time unit, and our 51N. Same can be said for 21, which is an impedance relay. But anyway, next slide. In the new standard, it came out in I'm not quite sure, in the 2000s, not the new standard, but the new upgrade allows you the IEEE device function number and has added some acronyms and allows the representation in several different ways. So now you have these microprocessor boxes that have a dozen or more functions within the box. This is the method here that I show on the screen that shows you those function numbers, defining what the actual function is. 21 zone 1, 21 zone 2, 21 zone 3, et cetera, and the connections that it may have to other devices. So, like you have a RS-232, you have an alarm to an R2U, you have an IRIG-B input, so forth and so on. And another one is a list box method for showing what's in a particular relay. Again, you have CT connections, VT connections, and you have a pilot scheme, 85 POTT. But the point I'm saying, the list box method for representing multiple functions, you have a lot of new stuff that has been added to the standard that allows such a thorough description. And to close it all, we have the standard 315. It's still 1975. I guess it was reaffirmed in 1993. But graphical symbols for electrical and electronic diagrams. Actually, I believe most everything you see in here, we say IEEE and IEC. Most of the IEC quantities are in the stated standard. They are not commonly used. But here it does you really want to learn the IEC standards as well, because a lot of what you may encounter in your careers will show things in this symbology. You have the IEEE, which is predominantly the U.S. and somewhat in Canada, but IEC is the rest of the world. But you have your normally open contact and your normally closed contact in Form Cs, and you got your transformer representation as shown down there. I've always liked the underground cable where you have a line under a ground symbol for the IEC standard. But it just is an example of how you take a set of engineers, put them in two different rooms, how they come up with something clever and good, but in two different ways. So,
okay. Hi, Elmo. Thank you so much. I actually do have a question, Elmo. It says, define POTT versus PUTT, and please compare the two.
Sure. I'm sorry I missed that. I kept looking down there. Okay. POTT is permissive overreach, and PUTT is permissive underreach. And permissive underreach is where you would use an underreaching zone, in particular zone 1. If you have a zone 1 operation, you send a permission to the remote in to trip. And normally, if you have a zone 1 operation, that would be the case. And at the remote end, you would have to receive permission, but you trip on an overreaching setting. It's under reach to send the permission, but it still will trip with permission and the operation of an overreaching zone. All right, but where a problem might occur with a PUTT scheme is that if the remote breaker is open, it can't detect the line in fault beyond the setting of the zone 1. POTT addresses that because you're using an overreaching zone to send permission, and likewise you have to receive permission and you trip with an overreaching zone. I hope that clears it up.
Elmo, the TT part of POTT and PUTT, TT stands for?
Transfer trip.
Transfer trip. Okay. I've got another question. What is the difference between static and electromechanical relays?
Static or solid state. In other words, they're built with solid state components. Transistors.
Okay. I've got another one about pot and putt. What is the typical protection that uses this scheme other than distance for POTT or PUTT?
Well, it would be ground instantaneous overcurrent direction. Directional ground instantaneous overcurrent.
Okay. Let's see, they're coming in. Hold on just a minute. Oh my goodness. Let's see. How are the low impedance and high impedance different in operation?
The high impedance, first there is a high impedance is a single element device that you basically, before coming into the relay, you sum all the currents, and the requirement is that all CTs have to be the same ratio, and of very similar characteristic, and you sum all these quantities up, which should, for a non-faulted condition, would of course be 0, and you go through one operating element to operate. And you push that current through a high impedance. So for example, if you had a 1 amp differential current going through 1500 ohms, you're going to generate 1500 volts. Therefore, it needs to be protected with a varistor or some type of voltage limiter, and that you also have that device as part of the relay. And it's an economical way of providing bus protection, and it's secure, but you are restricted. Again, like I say, of the CTs need to be all of the same ratio. Now, a low impedance method generally allows you you have a input. It's a let's call it a multi-restraining device. You have an input from each CT, but that each CT input can be handled with a internal transformer or a internal transformer type calculation to allow you to use different CT ratios. And rather than and again, you put all the CTs on the same primary base and work at primary level quantities, if you will, in your calculations. And but the differential principle is still the same. Ideally, they should all add up to 0. But their big advantage is that you can have multiple CT ratios being used, and as well as a slope type curve is generally associated with it, rather than just an operating threshold as is with the high impedance.
Okay. What impact will the IEC 61850 standard have on existing relaying protocols?
Well, the 61850 let me put it this way. First, the 61850, IEC 61850 is not just a protocol. It's a engineering design standard, and if I can say that a protocol is part of it, but it's a design standard that if the protection is designed with the 61850 in mind, you have a large number of logical nodes. I'm trying to think of a way to explain it without the appropriate graphics here, so you got to be patient with me here. It allows you to model physical devices, and a relay is a physical device. A circuit breaker is a physical device. So I model my relay with logical devices or logical nodes, and if I have a overcurrent unit that I want to operate, this logical node is referred to as a PTOC in 61850 logical node terminology, and that PTOC has certain characteristics that define it, and I would map data from that PTOC to a circuit breaker, which is defined as a which its model is defined as an XCBR, and it has certain characteristics. So it allows me to do, I guess the best way to say it is point-to-point wiring, but in a logical sense. I'm taking data from one and sending it to the other. The other reads that data and will act upon it appropriately. So it's certainly the protocol of the future. I mean, the 61850 standard itself allows interoperability between multi-vendors and well, between multi-vendor products. A good example would be the TVA Bradley 500 kV Bradley substation, which is a 61850 substation between ABB, Siemens, and GE.
Okay. I have a question. Explain voltage polarization and current polarization.
All right. Polarization, a polarizing quantity, as I said, is a quantity which is the reference quantity. It's to which you reference the fault current to. All right. And what is characteristic of a quantity is that its phasor representation does not change, and so you can reliably refer to it. Voltage is typically the 3V0 or 3V2, the negative sequence voltage, or the zero sequence voltage measured at the relocation. Regardless of whether the fault's on one side of the bus where the relay is applied or the other, the voltage quantity will not change, and you have to be familiar with symmetrical components to look at how that works. A current polarizing quantity comes from a transformer, and I guess the root of it is a transformer with a delta winding. And of course, the current that circulates inside a delta winding during a fault condition, and the non-loaded current. There is a circulating current in the delta winding. You have, let's say, high winding and low winding. You have the delta winding. And in that fault condition, the difference between the high winding and the low winding is what's flowing in the delta winding, and that is the polarizing quantity. Now, it can be measured by measuring what the ground current is in the neutral of the two neutrals of the high voltage winding and the low voltage winding sum. It can be measured there, but of course there are some constraints in measuring it well, let's just leave it at that. There are constraints. You have to come back for the polarizing course.
Okay, I've got another one. Is there any difference in the CT connections for both an electromechanical and the microprocessor relay?
No. It's all the same principle.
Okay. Let's see, pilot protection question. The communication channel delay between relays are more than the time required for the electrons. How can we protect the transmission line without any damage?
Well, that's a good question.
I didn't think of it, just so you know. It wasn't me.
Well, I'm not quite sure what the person is asking, but there is always, I mean, you have a fault condition, there is always going to be a certain amount of damage or contamination, if you will, due to it. And actually, in general, it's you have that arc in the fault, and the longer it's there, the more damage it's going to do. It's going to be a function of the square of the time, or the square of the current times the time, or something like that, if you leave it on too long. Now, clearing a fault in a cycle or 2 cycles, all right, a transmission line fault, all right, generally does not do, let's say, measurable damage. It's usually some type of flashover of an insulator or something like that due to contamination, or a momentary breakdown in insulation during a lightning storm, or a tree bumping into a line, or something like that. But that's why we strive for high speed in some cases, or reasonably high speed. But more than that, you want to try to clear it as fast as possible. I'm not sure the exact what the guy's questioning, but you trip what you can direct without that's the reason we have zone 1. We determine a fault, we trip fast, and if you have to use the communication channel, then you have to use the communication channel to get simultaneous tripping.
Okay, I'm gonna ask you one more question, Elmo, and then there's a lot of questions that have come in, and we will respond to any question that we haven't asked through email. We have a record of these questions and can get back to you. So if we haven't answered it on the phone and through the webinar, just keep an eye out for your email, and Elmo will respond to you directly. The last question that I have is, in order to establish redundancy in a protection network, is it necessary to use 2 relays, or are the new functions available in the modern relays able to provide redundancy?
Let's say redundancy, you need at least 2 boxes. Let me put it that way, where you can do some functions in one and some other functions in the other, or the same functions in the other, however you want to do it. But the moment you put it down to one box with multiple functions, you have the problem of that box failing itself, or something in the protection team's path, the CT or the voltage transformer which drives it, and so forth and so on. So you have to look at the application in total. And whereas in times past, electromechanical relays were used because electromechanical relays were discrete relays. You had zone 1, 2, and 3. The application of the whole other panel of zone 1, 2, 3 and pilot was not always used. But with the modern relays, you have a lot of stuff in one box. You can do a lot, but you need at least 2 boxes. And how you distribute the functions on them really depends on the application.
Okay, thank you, Elmo. I appreciate you taking time to answer so many questions. As I said, we will try to respond to the remaining questions via email after the webinar. You will receive an email tomorrow with a link to the recorded archives. I know that there were some audio problems for a couple of you out there, and you should be able to view the archive and get full audio. So thank you so much for joining us on our first webinar of the 2012 Protective Relay webinar series. We have enjoyed it. I hope you have too, and we look forward to seeing you at the next one.